thanks everyone for turning up, and sorry about the slight delay. Computers, who would trust them at all? Swapping over cables, they don't get happy and stuff. So what are we going to talk about here? So I want to sort of cover performance today. Now, who thinks it's difficult to write code with good performance? Is it hard? Do we struggle with it a bit at times? Well, I think we definitely struggle with it, especially if your normal approach to development is this. And unfortunately, this is a very common way that we do development. So we cut and paste stuff. Does it work? Do we really know what's going on? It's kind of bad how things happen. Well, I think there's an even bigger problem. We kind of live in the era of what I call this, resume-driven development. We want to extend our CV, our resume, and we keep adding technologies all the time. Do we really understand what's going on under the hood? Do we use things well? And as we put layers and layers and layers and layers of stuff on, we take up a lot of time with this. So I want to strip this right back and sort of look at, well, what is important and why should we be doing this? But sort of let's put it in context a little bit. Anyone heard of the ITRS? These people, this is the hardware industry who get together every now and again, and they look at what are the future trends, where are we going to? And the last time they got together was 2015. They produced this report, and they're looking at the growth in the use of technology and computing in the world. There's a bit of a staggering finding from this. If we continue on our current trajectory of how we're using software and the way we're building it, by 2040, there's not enough energy production on the planet to run our computers. Interesting. What are we going to do? And so I think like, we have exceeded what the airline industry now consumes as computing. This is our data centers alone, not including our mobile phones, everything else we do with it. So this whole thing of don't worry about performance, we'll just upgrade and we'll be fine, tends not to wash sometimes. So let's sort of dig in and go into a bit more detail on this, and particularly how do we design for performance if we want to actually care about this and how we're going to go forward. What I'm going to cover is 4 basic things. I'm going to cover a little bit about what is performance. What does it mean to be clean and representative? Some of this talk originally spun out. I did this first a few years ago. I was asked to do it at a domain-driven design conference, and it's actually very key to a lot of what's going on because modeling is at the heart of this. I'll look at how do we implement efficient models, and particularly how do we performance test them at the end of the day. It's not going to be a whole pile of bit twiddling and little tricks and stuff. It's actually just some pretty fundamental, simple things that we need to do to build systems that have good performance. And I happen to work in my day job for companies all around the world who build some of the highest performance systems out there, like seeing literally millions of transactions per second, and it's not actually that weird. Some of the code, when you see this stuff, is not what people expect. It's actually very clean, it's very readable, it's very understandable, and there's some very good reasons for why that is. It's not this weird, wacky world, but it's something that very few people get to see, and so they've got their expectations of performance being something else. So let's get stuck straight in. What is performance, and where does it all come from? What are we sort of talking about when we look at this? So let's take a step back and look at a bit of the history, and sort of particularly, anyone heard of Moore's Law? It's been around a little while. Again, let's look at the history of that, for example. So if we look back over time, originally, 1965, this is when Gordon Moore, one of the co-founders of Intel, started talking about some of these things that he was discovering that transistor densities were doubling every year. So we're packing more and more into our chips, and many people think Moore's Law is about the speed of our CPUs. Well, Gordon Moore was actually talking about transistor density. 10 years later, he revised this statement, and he says now they're doubling about once every 2 years, not once every year. So it changed a little bit. But around this stage, a different person made a statement that most people assume is Moore's Law, and that was David House, who also was one of the executives at Intel. And he observed that CPUs are doubling roughly every 18 months. And that's to do with the transistors getting denser, we're packing them in more, but they were also getting more efficient and better designed. And this is kind of something that's continued for decades. So from sort of the early 60s right through until quite recently, this did hold true. We were seeing speed-ups happening in the order of a doubling every 18 months. Over a 5-decade period, we've seen a 6-fold or a 6 orders of magnitude increase in our CPU speed. So we got used to this getting better, getting better, getting better. So that was kind of nice until things started to happen. Herb Sutter wrote a famous paper called The Free Lunch is Over. And what he was pointing out is the normal assumption of Moore's Law being that we're getting CPUs getting faster every 18 months to be doubling in speed was no longer holding. What had happened is we had run into this thermal wall, whereby to make our CPUs faster, we were increasing the clock speed. And if you increase the clock speed, you end up with a problem ultimately, because by increasing the clock speed, you've got to increase the voltage to get a proportional increase in clock speed. This unfortunately causes tripling of the heat that's generated. So we end up in this runaway problem that we can't get away from. We can't dissipate the heat. And around about this period, around 2005, we stopped seeing CPUs get faster in clock speed. This sort of topped out at around 4 to 5 gigahertz, and notice it hasn't really gone any higher since then. And a pragmatic limit is around about 3 gigahertz when you got multi-core, because you're trying to dissipate the heat from many cores at the same time. So what we found was Moore's Law was still holding. We were getting the true doubling of transistor density still happening every 2 years, but our CPUs weren't getting faster. So what Herb was saying is we need to go parallel. So parallel is the future, multi-core is the future. So we went forward from that, and we did start getting many more cores in our CPUs, but we started using that transistor budget for many other things as well, which I'll get around to in a second. Then we actually discovered that we run out of steam on that. Going through to 2016, Intel disbanded Tick-Tock. This is where they realized as we made things smaller and smaller, it became very difficult to make things that were small. Notice how we've got the 14 nanometers, and it hasn't moved forward from Intel for a number of years. There's the 14 nanometer plus, the plus plus, we're refining, we haven't got smaller. We're still waiting on the 10 and 7 nanometer to be delivered. Maybe AMD is going to deliver a 7 nanometer next year. But as we go below 10 nanometers, it gets incredibly difficult, and we are slowing down. So we're running out of the transistor budget as well as the CPU clock speed. I had this interesting problem. So we really have screeched to the ends of Moore's Law. What happened to that transistor budget? We didn't get cores just. We did get cores, but we got lots of cache. We got bigger caches, and we also got much smarter CPUs. We got many more execution units in them. I'll talk about that a little bit later. We got branch predictors. In fact, the latest AMD chips have got machine learning in their branch predictors to predict where our code's going. All of these things are getting incredibly smart. That ended up in a little bit of a problem this year. Google discovered with Spectre Meltdown that these were security issues. So we spent 10 years plus investing in making our CPUs really smart, to then discovered these really smart CPUs are really good to exploit. So we went on this sort of kind of ride where things got faster and faster and faster. Then it slowed down, and then it's gone backwards. This year, we have seen CPUs slow down. If you apply the microcode patches for the mitigations against Spectre Meltdown, you have slower servers than you had last year. So the free lunch is more than over. In fact, they're coming and charging us now. And there's no sign that it's going to get much better. So we need to think a little bit differently about this. Often, your boss will come along or your customers come along and goes, make it faster. Like, we've all heard this. Like somebody says, our software is not fast. What does fast mean? Let's get back and be a little bit more scientific about this. Fast is kind of a nebulous concept. It's not something we can put units on, so let's turn it into something that we can actually quantify. We've got to start talking about things like throughput. How many units of something can we do per unit of time? So when somebody says to you, make it faster, you need to start quantifying that. And so we know what we can measure. So can I do 10 transactions in a second? Can I move it up to 15 transactions per second? Whatever it happens to be. We need to have units of something over a period of time to start measuring. We also need to think in terms of response time, or latency as people will call it. So how long does it take to do something? And a good system, as well designed, will be if you increase the resources applied to it, you will get a proportional increase in the amount of throughput you get or a proportional decrease in the response time it takes for the system to respond. Now we can quantify what we mean by performance. We can start to make things better through this. So let's look at some of the fundamentals behind this. There's some math behind this that's been around for a long time that's actually quite easy to get our heads around. Queuing theory. 100-plus-year-old math with the work of Erlang that's been further refined. We end up, when we apply load to systems, they all follow this sort of trajectory, where utilization is the amount of the thing you're using, what percentage of its capacity are used at any given point in time, then that can be tracked directly to response time of the system. And it's a very simple probability thing. So if you're using 50% of a resource and you turn up to use it, there's a 50% chance probability it will be in use when you go to use it, so you have to wait and you have to take your turn to use it. The more you increase the usage, the higher this probability gets, and it starts to compound. So systems can look all great. So we can spend a lot of our time in this nice world down here. It all looks great. We apply more and more load, and then it goes wrong. And this is where systems will behave. They don't behave linearly like we expect. We apply load, and then all of a sudden they can come unresponsive. They go up this hockey stick. Now, this sort of thing appears in lots of places. This is an example of response time to a system. The same things happen in our load factors, in our hash maps and dictionaries. And we'll start to see that lots of this math appears in lots of places, but it's all common. It's often given different names, but it's very similar in its behavior. So one of the first pro tips to take away from this is make sure you have enough capacity. You don't want to overutilize anything, and that becomes fundamental to making something responsive. If you're running at near max capacity, anything else you want to do will have to wait. And by waiting, you then increase the response time and you slow down and being responsive. This applies at all sorts of levels. Now, the previous graph was based upon some math where you have to work out exactly the characteristics of your system. It happened to be a thing called an MD1 if you're interested in Kendall notation and stuff like that, but I'm not going to go into that now. There's a much simpler refinement came along 50 years later with the work of John Little, and a thing that became termed as Little's Law, and this becomes common and we can see it everywhere. I'm going to try and show you some examples with accessing memory where this really starts to matter. You may have seen this very simple law before. 3 variables we're dealing with, really nice and simple. In the lean world, you'll hear about this a lot. Like if anybody's practicing Agile and you don't fundamentally understand this formula, I'd say you're not practicing Agile, you're doing cargo cultism. If you're doing stand-ups and scrums and all of this ceremony and you don't understand this formula, you are missing the point of Agile. And what they're talking about here is that the work in progress or your ability to react in any situation is all down to your cycle time. Shortening cycle times, getting better feedback faster is key to being agile. This is why we have continuous integration. We find out if we break the system very quickly, not after we release it and later. So the sooner we get the feedback, the better. Everything should give us feedback quickly so we can react and react in a timely manner. Then we can work in a better way. So you see this formula appear in lots of places. Now, another variant of this, it's exactly the same mathematics under a different name. If you work in networking, you have to tune the sizes of your buffers to get your ideal throughput and use this formula with bandwidth delay product. It's Little's Law with different name. The bytes in flight, the length, equals the bandwidth times the latency, which is your throughput, and your cycle time is what you're dealing with at this level. Exactly the same sort of problem. So we started looking at this. How can we work out how much memory we can access from a single CPU? So taking a very simple formula and applying into this, if we want to access a long or 64-bit number, that's 8 bytes at a given time, if we assume main memory access is an average of 100 nanoseconds, we can only do 800 megabytes per second because we only have 10 line feed buffers in our CPU. We have the ability to concurrently track 10 cache misses at a time. That greatly limits us because our servers are capable of 50 to 100 gigabytes per second per CPU. So we're not using this correctly. I'm going to come back to this and see, well, how we can change a little bit of what we do, play with this mathematics, get much better throughput. Now, we could get better throughput if we go parallel. Like if one CPU can only use 800 megabytes per second at that sort of rate, I can use lots of CPUs and go faster. We end up with some other laws that come into play. So Amdahl's law comes in at this stage. You've probably all heard of this at different stages. It's actually based on a paper that Gene Amdahl wrote called Amdahl's argument. And his argument was quite simple. He wanted to scare people off writing parallel programs. He wanted to prove the point how difficult it was. Not that he wanted people to do this. He sold very fast, single-threaded mainframes and he was competing with IBM. He didn't want these new microcomputers and mini-computers doing really well. He wanted people to stay on mainframes. And his point is quite simple. Is if you've got a job and you need to split the job up to go parallel, your speed up is proportional to how much you can actually do in parallel and restricted by the bit you can't do in parallel. So if I can do A in parallel, I've got 4 CPUs, I can get the job done quicker. My system can be more responsive, and then I can get more throughput. If A can't be done in parallel, but B can, I can get much less of a speed up. So the percentage really matters. How does this percentage play out when we look at different options? Like if 50% of your algorithm can be done parallel and 50% can't, you cannot get greater than a 2x speed up. You're just limited. What about if you've got an algorithm that's 95% can be done in parallel, but only 5% cannot be? You cannot go greater than a 20x speed up. So the point is showing that if you have an algorithm with any contention point, you're fundamentally limited in your ability to scale it by throwing process on the other side. So it becomes an interesting thing. But he made this point just to scare you. He didn't actually test it a lot. And when some people came along to test it, they actually found out the world was worse than he predicted. So Xerox PARC, a guy called Neil Gunther, an Australian, was working there, trying to do parallel speed up and realized he couldn't achieve this. His work led to another interesting law called universal scalability law. It gives you a better picture of what's actually going on. The contention, the alpha in this, is exactly what Amdahl was talking about. We're limited in their ability to scale based upon contention, but he realized there was another important component, and that other important component is the coherence penalty. It's the time to reach agreement between all the participants in any given algorithm. This becomes really important, and it means that you cannot speed up if you cannot communicate fast enough. What's fascinating about this formula has shown up in other places as well. Anybody read The Mythical Man Month? Brooks' Law? Brooks' Law is universal scalability law discovered in another domain, given another name. The math is ubiquitous. This sort of stuff appears in lots and lots of places. So what's it look like on a graph? We've got the Amdahl's law case for this is an algorithm that is 95% can go parallel, and I'm going to throw more and more CPUs at it. What can happen? I then add in 150 microseconds of latency for agreement. Let's say you're working in a cluster and the machines are communicating with each other across a reasonably fast network. Look, it gets faster and faster and faster, and then the coherence penalty starts to take over and dominate, and it'll start to slow down. You don't get the speed up even that Amdahl predicted. This is what Gunther discovered. So we get very limited in what we can do. So you got to think of how do we deal with agreement, how do we deal with the coherence. Now let's apply this to a real example. I'm not going to hit you with lots of math. We're going to move on to something a bit more practical. So let's take a real system. This is a system I measured. Now, have a guess what this system is. I'm applying multiple CPUs here. So I'm adding CPUs, and I'm looking at the average response time of a transaction into the system. And it's going up as I add CPUs. This implies that I'm not getting any parallel speed up at all because it's going up linearly. This is an algorithm that is 100% contended. It is the worst case under Amdahl's law. What do we think it is? Sorry? Counter? No, it's not a counter. But kind of. I/O is involved in it, but it's something that you probably, I can guarantee virtually everybody in this room has used at some stage. Close. It's the mean logging duration of pretty much every Java logging framework. I've seen people invest so much time into making their system scale, and they're logging. Like, I've seen code bases that I cannot see the actual logic for the lines of logging statements that are in there. It's like, please learn to use a debugger or some other means of finding out what your code does. Because littering your code with log statements, you end up with this as a problem. Amdahl's law comes and hunts you down. And sorry, there is no escape. It's math. It has no mercy. It will come and get you. So kind of being aware. And what's happening is why this is going like this is everything's writing into it, and it's got a great big lock around it. It's protecting a single buffer that you're writing into, and then that's getting written to disk occasionally. So it's even worse from, if you look at it over time in a histogram, this is just the average. The average is actually hiding how nasty it really is, and I'll come back to some of that later. So what does it mean to be clean and representative? Getting around to modeling. I'm dyslexic. I love to look things up in a dictionary to get my head around whether we have given things the right name. And I keep finding in computing we give things terrible names. We give things the wrong names all the time. So people talk about clean code. What does clean code mean? Well, let's look up in the Oxford English Dictionary. And clean means morally uncontaminated, pure, and innocent. Most code I see in most enterprises is none of that. It is not uncontaminated. It is dirty and disgusting and quite unpleasant. So I really wouldn't call it clean code in any sort of way. That's kind of like a bit of fun on it, but let's look at what representative mean as well. It should be a portrayal of something. It should be a really good description of what's going on. If we're producing a model, we've got to think of what are we capturing in code. I like to think of code, it's the place where we capture our best understanding of something. We can document stuff. Documents go out of date. They don't get updated. People forget about them. Code is where we capture stuff. So if you're calling business things in your code single character names, please get over that. And by the way, that is not a performance improvement. It was a performance improvement in the sort of 1970s and 80s whenever we didn't have much memory to store stuff, including your code. These days, you can give something a big, nice, descriptive name. It will not slow your code down. So let's make things sort of representative, make it a good example of what we want to have in here. Now, ultimately, when we write code, we'll often talk about abstractions. I hear this all of the time. So what do I think of abstractions in generally? So steal a little bit from movies, and I like movies in general. Something from Fight Club. First rule of abstractions, don't use abstractions. People are, what's he on about? Second rule of abstractions, don't use them. Usually at this point, people get a bit pissed at me, and if anybody takes a picture of this later and tweets it, I'll get a huge amount of shit on Twitter with people giving me a hard time. Why am I saying this is we rush into it, and we often don't understand abstractions. Right, let's soften this off a bit. Yeah, so we can use abstractions, but we've got to think about when we're using them. So you must have some simple rules around. So only start abstracting when you see three things that are the same. They have to be the same thing to be worth doing. Don't try to be smart up front and sort of think, well, this is my first time doing this. I'm going to abstract because I'm going to be thinking of the future. You're going to be wrong usually. Like, get over the fact we're all kind of defective carbon units. We make mistakes. You're better off doing it a few times until you've got a pretty good idea where you're going. It's incredibly arrogant to think up front that the first time you do something, you're going to put in a whole pile of abstractions to describe this for the future. Think about what that says about your personality. Try to twist it around. Be a bit more humble with it and say, well, okay, let me do this a few times until I've really got a good handle on it. Then you'll start to make better decisions on this. But also think about all abstractions have to pay for themselves. Nothing's free. If we're going to start applying abstractions in our ways of working, they must be paying for themselves because they're going to have a cost. They may have a cost in some sort of interaction. They may have a cost at a semantic level. And so we've got to think about it. And a common one I often see is people start drying out code, especially drying it out too much. And they start creating abstractions that really are not representative of what's going on. And that can lead to lots of coupling. And in many cases, coupling is much worse than having copied something. If you're a fan of DDD in any ways, like when do you dry stuff out? When do you think about coupling stuff or decoupling stuff? If you're inside the same bounded context, that's perfect. Dry it out. Do the right sort of thing. Trying to dry things out across bounded context, that can get you into a whole world of pain and a lot of coupling. Because those things should be able to evolve and react independently, to be worked on by different teams, released at different times. We've got to break the coupling. If we start drying these things out, we often get problems with the coupling, and it comes and gets us. And say, for example, if you're just in an object-oriented world, we put a type in place, and then we've got polymorphism for it. When you've got one instance of a type, our compilers can do a lot to make it very efficient. When you get two instances, it's actually still pretty good. So we go from being monomorphic to bimorphic. That works quite nicely. As soon as you go to 3 or more, typically, we end up in a thing called being megamorphic, and we have to put jump tables in place. We can't inline as well. Our compilers get limited in what we do. So just don't rush to some of this stuff. It has quite a cost, and it starts to build up after a while. And when it's not representative, it becomes the smell. It gets confusing. I worked on a system a while ago where I was trying to find the clock in the system, and there's a particular functional programmer who was working on this. I won't name the person through shame, and I couldn't find the clock in the system. And eventually I did find it by tracing through what was going on, and this thing was a supplier of longs. And yes, I can understand from an abstraction point of view that, yes, a long that represents the number of milliseconds since epoch is a way of representing a clock, but it's not particularly useful. It also meant this whole thing was megamorphic all over the place because it was used in a number of other ways. So think carefully about this sort of stuff. And kind of question when you use big frameworks. Sometimes we get lured into this. We use frameworks a lot. We get a bit carried away. I like to think of it a bit like this. I used to backpack when I was younger, took time off, and you learn very quickly about, you don't carry much. 3 things at most is what you need. Wash one, wear one, dry one. It makes it nice and light. But you get people who kind of do this sort of thing. They'll bring loads and loads of stuff. We get like that with our projects. Like, I see Java projects where people start out and they're installing all of these frameworks and libraries that they're using. And they think, what are you doing yet? What's the project for? Like, think about what you're building before you go get all of the kit. It makes things a lot easier. Then you won't get hit with a lot of the overhead, because if you add the things in one by one, you know the impact it's having, you know the cost of it, you start to realize, okay, I have wasted too much here, I've spent less there, whatever it has to be. If you work in the airline industry or spaceflight or anything, everything that goes onto a craft has to pay for itself. Otherwise, you end up carrying this cost and weight and fuel for no good reason. Abstractions have gone so crazy in our industry, we've even got the law of leaky abstractions by Joe Spolsky, the guy who worked on Microsoft back in the day, or Excel back in Microsoft. And he points out that it's all because the detail of the underlying is there. It's a complexity that cannot be ignored. This is actually where you've got abstraction wrong. An abstraction should be precise. Taking from Dijkstra has a much better description. The purpose of abstracting is not to be vague, but to create a new semantic level in which we can be absolutely precise. Yet we get people abstracting, saying, oh, I'm hiding the detail. That's not the point. The point is to give you more precision about what you're doing. So that's kind of weird. Let's make this a little bit more concrete. So can we abstract how our memory systems work in our computers? They're incredibly complex these days, but look at it from the design that's been put in place by our hardware friends. What abstractions are they offering us? And then let's look at the detail behind it. Well, they're doing it very simply. They're making design decision based upon 3 bets. They're expecting our code to follow these 3 possible bets. One is a temporal bet. So we're going to use things together close in time. That's what most people understand how a cache works is. If I've used it recently, I go to use it again. It's in the cache. I get to save from that. That's a benefit. That's the obvious one. There's less obvious ones, such as the spatial bet. So things that are close together are used together. And this is very fundamental to some of the rest of the design I'm going to come around to. And the third one being, there's a pattern bet. So that if you're going to access something, you're going to access it in a predictable pattern of behavior. That pattern can be learned and applied. That's the abstraction that our hardware friends give us for how we use memory. It's not that it is totally random access. That whole thing is memory is not totally random access. And let's look at some figures to actually prove that. So I'm going to write a micro benchmark that's going to test access patterns to memory and show you that just taking any random pattern is not the same as having an arbitrary pattern that is known. So here's a number of different ways we can access memory. So let's go through a big array from the beginning to the end, adding up all of the values in that array. And if I do that in a sequential pattern, it is less than 1 nanosecond, or less than 1 nanosecond per step going through that array. I'll explain why that is in a second. As we go up with different patterns, like let's stay random within an operating system page, touching all of the same words, then moving on to the next operating system page, we're going up to 2.7 nanoseconds per operation. Let's be random in a page, but the next step I take is dependent on the previous step. So I can't race ahead. I can't use the concurrency that's in some of our processors. Or let's go sort of random around a whole heap, which is the whole array, or random around the whole array feeding in from the last value. So there's a number of different ways of doing this, 5 different ways. Note the last one, 89. That's almost 90 nanoseconds. That's on a pretty fast machine as well. So we have 2 orders of magnitude between going through something completely sequential, through to going through something, doing all the same number of steps, and I'm going to actually use the same number of CPU instructions to do it, where the pattern is random, where you can't take a step till you reach the next step. This is how our data structures are designed starts to exhibit this. And this ends up with the problem of why, whenever we access memory, we get these very different behaviors. So feed this back into the formula from earlier. So this bytes in flight equals bandwidth times latency. So if we had 80 bytes, which was 8 times, or sort of 10 times 8 bytes for longs, 100 nanoseconds to memory with the 10 line feed buffers, I can only get 800 megabytes per second. Now, how about if I change the latency? So if I'm prefetching the memory before I get to it, by prefetching into the L3 cache. And this is what our hardware prefetchers will do when our pattern is known. So a sequential pattern through memory, walking with given steps that are known forwards or backwards, the hardware can prefetch that for us. So it starts prefetching, that changes the latency. Now we're up to 5.3 gigabytes per second. That's quite a step up. And then we play it to the other bet, the spatial bet. It doesn't just fetch individual words, it fetches cache lines. And a cache line is 64 bytes on an Intel CPU. So they're all coming in at the same time. And so you think about the sequential case from the beginning to the end. Each operation is going out, it's already been prefetched, and it's prefetching 64 bytes at a time. Now we're up to 42.6 gigabytes per second. So there's a big difference. If you sort of think about that for a second, if you treat main memory like it's random access, it's really slow. If you treat it in a sequential fashion, it's really fast. What's the big takeaway from this is, normal memory is tape. All memory subsystems you'll find you access behave like tape. If it's a spinning disk, if it's an SSD, if it's main memory, you'll find that they're all very, very similar. Your memory access patterns start to matter, and they get us. And that's locally within one node. We can end up going across other nodes. So you go onto one of the very large boxes on Amazon these days, you get multiple CPU sockets. Each of those have tens of cores. Each of them have their own memory, but they're having to communicate with each other across a network. So that 100 nanoseconds case that was there, you need to add another 50 plus nanoseconds to that as you go across these hops. So it starts to go up to become more and more. So it starts to matter how we access our memory. Like, why was it able to do so many steps at a time, especially when it's prefetching like this? Well, inside our CPUs, there's loads of execution units. We don't have one ALU anymore. If we have a Haswell processor, this is going back to 2013 onwards, we have got 8 ports on those. Each of those can be executing an instruction at the same time. So that is sort of 8 instructions on a single thread. at the same time, and our programs get to do a lot of this in parallel. There's 4 things that can do math. There's only 2 things that can do branches. See over here, I've got a branch unit. This was newly added in 2015, and we have a branch unit here that was available before. It used to be we could do 4 mathematical operations, or no, so 3 mathematical operations previous to 2013 on one branch, on branches ifs, whiles, fors, anything that causes a jump to happen. This goes forward, so we can do 4 times the math now that we can off the branches, and just how things go forward. It becomes a much faster way of doing stuff, and we can look at our algorithms and we can make them faster, and there's lots of cool stuff we can do. But actually, that is not the main thing. The main thing is our cache misses. Because if you've got all of these execution units, they're all running in parallel, even on a single thread. A single cache miss to main memory now is a lost opportunity where you could have executed about 1,000 CPU instructions. So your memory layout matters more than anything. What's this all mean? That may seem like, wow, that's all kind of crazy stuff. Let's look at what this means for our models. But it comes down to coupling and cohesion, things like this. We've got to get things together that are important to be kept together. These basic design concepts start to really matter. Like, stop thinking of your classes, your objects, whatever they are, as property bags. You think about what needs to change together, what needs to be accessed together. These are the things that has to start to matter. So you've got to respect the locality of reference to keep these things together. Simple ways to think about some of this is, if you're in the data structures, could you implement a good B tree or B plus tree in your language? If anybody here's Java programmers, you're kind of out of luck. It really sucks for doing some of this stuff well. C, C#, a few other languages can do this much, much better. So if you want to get down to lower levels, it's the data structures start to matter. And the data structures end up being used in our relationships. So I work a lot in finance where we deal with quite complex models that may appear simple. So I've got an order, I've got orders in the order book, but it gets more complicated. There's 2 sides to it. There's buyers and sellers, so you've got relationships for bids and offers. They're also qualified and sorted on price. You also have to take into account the time of arrival, so first in, first out. What data structures we end up picking for this starts to really matter. So knowing your data structures is one of the most important things to getting your models right. Everything isn't just a hash map or a list between it. There's many types of maps, many types of trees, data structures. This is where we get a lot of our performance. And the things that you learn in this space will stay with you for life. I started writing code in the early 1980s. I started professionally writing code around 1990. And since then, going forward, everything I've ever learned on data structures has never gone out of date. The numbers of times that I've learned frameworks, learned ways of working, at one stage I knew web logic really, really well. That is just a wasted time in my life that hasn't come back with any use at all. Stuff I've spent on learning trees and data structures and everything, it's been wonderful. It's come back and it's helped me so many times. And it's not that I need to know how to write them. It's that I need to know to pick the right one for the relationships that I'm dealing with. And when you come to things, when you look them up, please, please, please don't use strings as the ways of identifying things. Like, all of the entities in your systems, like your customers, your orders, anything you have, your people, stuff, and deals, give them surrogate keys. And longs are great for that. And you can start looking up and referencing things all by identity by using these keys, not strings. Don't use the strings to do this. It will really end up hurting you. When we start doing stuff, we've got to batch, we've got to get things together. So I'm going to whiz through some of the rest of this. So the more thing we had to do is we've got to amortize these costs. We've got to save ourselves the time when we're doing stuff. So whenever I came up with a disruptor, we had a pretty simple problem. What we were dealing with is we needed to amortize doing expensive things like writing to disk, writing to network, dealing with all of the things that's going on. Don't do the stupid things that a logging framework would do. If you put something in the middle that'll amortize this stuff, so rather than multiple producers all taking a lock to go to the underlying thing, store them up in some data structure that's going to be really efficient, and then have something that's batching things down. It makes it much, much more efficient, much greater throughput, much lower latency on average. We can get from being on that red line to the blue line by doing that. And by doing that, what you have to do is you've got to reduce the service time. And if by reducing the service time, you can reduce the utilization, and we end up on this. So how does it work out with batching? Well, you don't need to put 1,000 things into a batch. Say the cost of doing something is 100% for a single operation. If you put 2 things into that batch that writes to disk, 2 things that writes to the network, the cost for each of those 2 things is 50% of the cost of the operation. It's amortized. You put 4 things in, it's 25% for each of them. The biggest single win you get is going from 1 to 2 in a batch. Getting up to 10 to 20, and you're already most of the way to what you're ever going to get out of something. So you don't need big batches, you just need to start batching and start thinking about it. And once you're even single digits, you're doing really well. Branches are everywhere in our code. We need to try and trim them, get rid of them in different ways. What are the costs of them? Well, so we've got these 2 branch units, we've got all of these other units. Let's look at how our branches are predictable or not. A baseline, let's run through an array. I want to deal with numbers that are randomly generated between 0 and 1,000. If they're based on some conditions, something's going to happen. So my baseline is any given number that's greater than 0, I'm going to do something. That's my baseline value. I'll go through, how about if I organize the array so they're all sorted from 0 to 1,000, and I'm doing a thing where I'm going to do one thing on even, one thing on odd. They're going to go even, odd, even, odd, even, odd. That's predictable. It's actually pretty much the same cost. There's a little bit of error variance in it, but it's pretty much there. Now, randomly sort the array, boom, over 4 times. This is the sort of thing that starts to happen. How predictable is the things you're dealing with? It starts to matter. We've got to get our stuff organized, get it predictable. Predictable in memory access, predictable in our branches. Loops are kind of similar as well. Think about your loops as something that you've got to think about carefully about it. You've got to reread your code often. Probably the best thing I've learned in my career is how I work. And I've realized that if I write something down, be it a bit of code, be it an email, be it anything, don't finish it there and then. Park it, go off and do something else, come back later and reread it again. You'll see stuff that you didn't see the first time. You'll see ways of improving it. It's because it's just how our brains work. When we go to do something, you fill up your brain. It's just like a cache. Whenever you go to review something, you're actually playing back from your cache, not from what you've actually done. Go off, do something else. You've effectively flushed your cache. You come back to it again. You have to read it fresh. You will see the mistakes that you don't see before. Do that with your code. So work by working on something, leave it for a period of time, come back, review it, and have a pipeline of things going like this rather than discrete individual tasks. It gets a lot better. When you see your loops, you'll start to realize that our loops have instructions that are decoded. They end up going in our CPU. There's a cache inside our CPU. It's pretty small. It can't hold that much, so 1,500 operations in there. If your loops are bigger than that, you're churning through that cache. It's getting more and more expensive. So keep it small, keep it simple. There's an even smaller cache than that behind it, which is only 56 operations. So small, really nice tight loops are very fast, very neat. Those loops can't have more than 8 branches. They can't have a return inside the loop. Otherwise, they don't fit in those sort of cache. So you've got to kind of watch with some of this. So simple, elegant loops. Don't just keep throwing more and more code into them. And so think about craft your loops like good pros. Composition, like size matters here more than anything. So keep the thing small. Let your compiler put them together. Cliff Click talked about how size is the optimization. He was the guy who done the hotspot C2 compiler. He realized that if you can inline stuff, you can do really great things with it. Don't make your methods big. Don't make them verbose. Allow your compiler to assemble things rather than you put them together yourself. And so keep things very much single responsibility. APIs are a huge thing we can do a lot about. Like, take this monstrosity as an example. This is how you deal with the network in Java. If you want to read from sockets, you create a selector in the socket, and then you have to wait for work to be done. We have to do stuff like get a set of selected keys from that and then iterate over that. It's horribly painful. It allocates. It's really nasty. And look at it's like so much horrible code it makes your eyes bleed. You could have just redesigned that API and done something like this, like Slack now, and pass in the keys to be filled. It's much simpler, much more elegant, doesn't allocate. Just thinking about stuff. Like there's many, especially the old Java APIs, they're pretty terrible in their design and encourage the bad behavior. We need to have better examples of this. I'm about to run out of time, so I'm going to wrap up on this. So think of data separately. Don't do the whole sort of, we're going to deal with data by having rows and rows. Split it up, think of columns, access stuff in columns as options as well. So not necessarily in objects, have arrays of the fields that would be part of something. It becomes an easier way of dealing with something. You can go down and deal with, or you can even just sort and search within the rows themselves. It's much, much faster. We should be performance testing. To do that, we need to define our goals. We need to create baselines, like I showed in the previous examples, of how we measure to see where we're doing against those, and we've got to measure response time. So from here, I'm going to go towards the end, because I'm going to be out of time. So this was a presentation designed for an hour. I don't have an hour, so you're going to miss one of the sections. Grab me afterwards if you want a chance to catch up on that. So in summary, just try to make it clean. The cleaner we can make it, it's going to be easier to deal with at all the layers of our stack, including us as humans, and be able to deal with it. And if we get this right, so I started off by saying that some of the fastest systems in the world are actually really easy to understand. But one of the reasons they get to be really fast, and they're actually very fast to iterate and work on, is because they're based on good fundamentals. If you base things on good fundamentals, they become stuff that's easy to work with, easy to change. They're well decoupled. They've got good cohesion in all the places where they have to be. It makes it a lot easier to deal with and understand with. I'll leave you with this thought. Bill Lear, who built the Learjet, he had a great expression. He says that if it looks good, it'll fly good. It was also said by Kelly Johnson, who run the Skunk Works, produced things like the SR-71, the Blackbird. Very, very similar things. Is you get to find that in high-end engineering, it starts to look right. And I've found, looking at some of the highest performance code out there, I can almost tell now without profiling, because it just looks good, it looks elegant. If it looks weird and complicated, it's probably not going to be that fast or that nice. So it's not a surprising thing that we find out that is difficult in the end. So on that, I'll thank you very much, because I think I'm just about out of time.
Yeah, thank you, Martin.
Thanks.
Actually, someone is typing a question. Maybe you want to ask that like live? No. Oh, we have no time, so you have to answer that in Slack. After that, I'll show you the question later on.
Okay.
Yeah, well, maybe you can answer that.
Sure, what's the question?
Which resources can you suggest for learning performance optimization?
Oh, so which resources for learning? There's many places. I've been asked this question a number of times, and I was giving a course. It was actually down in Australia when it happened, and one of the people in the course suggested, like a lot of things we were talking about, a few people who sort of specialize in this space, where do they kind of hang out, and how could we get them to sort of come there more regularly? At that point, we found the Mechanical Sympathy group on Google. There's a number of people who will contribute and answer questions in there. Just reading the back history of that is kind of a good place to go do that. So I'll plug some books. Brendan Gregg's work, Systems Performance. He's the guy at Netflix who's been doing a lot of good work in this area. There's kind of a lot of kind of interesting things, but sort of a lot of the links from where to go start in the Mechanical Sympathy group. You can go find that. It's an open group on Google. Feel free to check it out and ask questions.
Yeah, someone else type in a question. Maybe you could just, instead of typing, just ask it. Where are you? Gaspers? No? Don't be afraid. Don't be shy. It's easy. No. Did you? Oh, you did. Right, okay. Does it make sense to write performance-critical code in high-level languages like Java or C# in the first place?
Oh, so that's a good question. So, it is a really interesting one. So I'll give you a real-world example that I've got first-hand experience of. I was asked to build a messaging system that was as fast as the fastest commercial messaging systems out there. And we decided initially to do it in Java. The reason we chose Java was not because we knew it was going to be fastest. It was because we knew the development time would be faster. So part of it is like, oh, how quickly can we iterate algorithms? And actually, the algorithms matter more than anything. So as I said in the talk, like a cache miss is worth about 1,000 CPU cycles that have been lost at a given point in time. We built this messaging system. We weren't just as fast as the fastest ones out there. We were well faster than them. We actually set a completely new level for the speeds of these things, and that was written in Java at that point. We then produced one that was written in C afterwards. We were able to get that to go even faster again. So ultimately in C and other languages, C++, you can go faster than, say, Java or C#, but it takes you a lot longer. Like I've found that there's a kind of interesting trade-off thing, and you see this a lot in financial trading now, where time to market is as important as your outright performance. So you may have an algorithm that, say, per unit of time can make X. If you were to write that in Java, you're going to get X. If you were to write it in C, you may get sort of 1.4 or 1.2X in that per unit of time. But with the writing it in a more productive language, you get it to market earlier, so you get more units of time to make from it. And as a result, it can actually be a more profitable overall algorithm. So getting there, and this is actually part of the feedback cycle. It's like Little's law is everywhere. Everything we interact with, we make better decisions if we get faster feedback. And part of the thing about getting the faster feedback is you can refine the algorithms quicker, and then once they stabilize, port them to something that can ultimately be faster, but it's more stable. Like, we see this in finance where something may get trialed in a language like Java, or it's I've even seen stuff done in Python. It's been kind of proven to work. It gets ported to Java or C++ where it's faster, works even better, and it still keeps on working and eventually gets fabricated into FPGAs or ASICs to be really, really fast. But the algorithm's proven in a way of working. So it's a kind of interesting way to evolve through these things. So yes, you can do really fast things, but you ultimately will not be as fast, but you have a bigger time burden in going with some of the others.
Okay, maybe one last question. Is Rust a killer for C and C++?
That is an excellent question. Rust, I think, is a pretty awesome language. I don't think it's there yet on the tooling and other things. And whenever I say I'm really fast in writing stuff in Java compared to writing stuff in C or Rust or other things, it's not Java. Be honest, Java sucks as a language. What is brilliant is Java, to me, is the worst language with the best toolchain. It's the tools, the language, the community, everything else is so good. That's what actually makes it incredibly productive. If Rust had the quality of tools that the Java community have, it would be pretty awesome. Many languages would be pretty awesome if they had that level of tooling and quality. I remember in the 1990s playing with all of the early C compilers, particularly C++. Some of them were really terrible. They're using things like CFront, where you took C++, you compiled it into C, and imagine debugging stuff that is actually, it's C, but it's been cross-compiled from something else. It's pretty nasty. And then we started getting native C++ compilers with native debuggers and everything. It became so much easier and nicer. Like, if any language is going to really win, it doesn't truly get there until the tools, until you get good testing, good profiling, good debugging, good editors, all of that sort of stuff, and a good community around it. Then it starts to get pretty awesome.
Thank you. I think we're totally out of time.